1.3, limits at infinity. This time we're going to look at limits as x approaches infinity or negative infinity. In this case, we're looking at what's happening at the ends of the graph. What is the end behavior of the function? Okay, so as, let's see, these ones, without a calculator, we're going to evaluate these. Now the first one, you may not know exactly what that function, that polynomial looks like. But as x approaches infinity, each of those terms, except for 11, is going to go towards infinity. So we look at our highest degree here, and that tells us that as we go to the far, far right end, it's the function, the y values are going to be approaching infinity. As we analyze the same function as x goes to negative infinity, okay, think about this portion of the graph only. As x goes to a negative infinity, the y values are going to be decreasing without bound, going towards negative infinity. Limit of e to the negative x. Hopefully you know what that graph looks like, but if you don't, it looks something like this. Okay, or you can think of 1 over e to the x. Either way, if you imagine it graphically or algebraically, as x goes to infinity, if you look at the graph, the y values are getting closer and closer to 0. And if you look at the function, if you let really big numbers go in for x, that bottom, that denominator, is going to get huge. So you have 1 over this huge number. Either way, 0. Okay, limit as x approaches negative infinity this time, we would be going towards infinity. Sine of x, you should know that graph, it oscillates back and forth between -1 and 1. So as x approaches infinity, it's not stopping, it's not kind of increasing without bound or leveling off towards a number. This one does not exist, okay, because it oscillates. In the next example, we have negative infinity. So we'd have negative infinity times -1, negative infinity times +1, oscillating back and forth in between those values. Again, it does not exist. Now this last one, it seems similar to E and F, but 1 over x, as x approaches infinity, that function, the y values, are approaching 0, and 0 times anything gives you 0. So if, like in the last example, you take the limit as x approaches infinity or negative infinity, and that limit equals a specific number, not infinity, it has to be a unique number, then that function has a horizontal asymptote at that value. Now remember, horizontal asymptotes are not discontinuities. The graph can cross them as many times as it wants. It's just showing you the end behavior on at least one part of the graph. Now, for your whisk, I'd like you to answer the question, how many horizontal asymptotes can a function have? All right, on to the next problem. Find the equations of any horizontal asymptotes of this function by analyzing the end behaviors of the graph. So what we're doing is we're taking the limit as x approaches infinity of arctan of x. Now, hopefully you know what that graph looks like. I'm sure that you do. Okay, it looks something like this, and it has these horizontal asymptotes on either side. If you don't know that, then you should at least know the graph of tangent of x, and think of where tangent of x has vertical asymptotes. As x approaches infinity, y approaches pi over 2. Now, as x approaches negative infinity of arctan of x, it approaches negative pi over 2. So that means that we have a horizontal asymptote at y equals pi over 2 and y equals negative pi over 2. And you're going to see that rational functions often have horizontal asymptotes. So in the first example, part A, the degree of the numerator is 2. The degree of the denominator is 3. That means that the bottom is going to grow so much faster than the top. So when we analyze something at limit as x approaches infinity of f of x, 3 billion over 5 billion, okay, but no, it's going to be more than billion. It's going to be whatever, quadrillion. It's going to be even higher, 1 power higher. The bottom is going to get faster and faster. Think of a small number on the top and a really, really large number on the bottom. That is going to get really close to 0. All right, let's clear that out. Okay, the limit as x approaches negative infinity. Okay, in the top we're going to have a positive number, and the bottom we're going to have a negative large number, larger. So we have 0. So this function has a horizontal asymptote at y equals 0. And you're going to see that anytime you have a degree of the denominator higher than the degree of the numerator, you're going to have a horizontal asymptote at y equals 0. In the next case, we have g of x. So if we take the limit as x approaches infinity of g of x, this time the degree of the numerator is exactly the same as the degree of the denominator. So you're going to have 3 billion over 5 billion. Okay, if you simplify that, you get 3/5. Now if we take limit as x approaches negative infinity, the top's going to be -3 over -5. So again, we have 3/5. So we have y equals 3/5 as a horizontal asymptote. For this last one, if we take the limit as x approaches infinity of h of x, the degree of the top is 3. The degree of the bottom is is 2. So the degree of the top is bigger. If you have a bigger number over a smaller number, that's just going to continue to grow, okay, and grow and grow and grow without bound. So as x approaches infinity, we have this +4 over -2. So we're going to be going towards negative infinity. The limit as x approaches negative infinity of h of x is at the top, we would have a negative number. At the bottom, we'd have a negative number. So in this case, it's going to be approaching positive infinity. So we will have no horizontal asymptotes in this example. We will have something else, and that'll be discussed in the next video. And some of you may wonder why I'm just kind of disregarding all the other terms. Well, when it comes to 3 billion or something even larger than that, 12 doesn't really matter. Okay, same as -x. And I can show you an algebraic way if you really care about that, but if not, that's all right. Have a good day.